In this video, I want to be a little more explicit about deriving the Maxwell relations from fundamental property relations. Let me first write the fundamental property relations, which we derived in earlier videos in this playlist. du is TdS minus PdV. dH is TdS plus VdP. dA is minus SDT minus PdV. And dG is minus SDT plus VdP. One way to look at these is that we had a state function u that could be calculated in terms of dq and dw, heat and work. And we decided to do Legendre transformations to define h, a, and g, which are functions that contain the same information as u, but rather have different natural variables. H may depend naturally on S and P, A on T and V, and G on T and P. Maxwell relations come from the fact that these are state functions. So if I have a state function f of x and y, then the following is true. The second derivative with respect to x and y is equal to the second derivative with respect to y and x. In other words, if you're taking what some might call a cross partial or a second derivative, the order doesn't matter. And so that means that d squared u ds dv would equal d squared u dv ds. So let's calculate what that is. Copy this. So du dv at constant s is going to equal minus p d squared u ds dv is going to equal minus dp ds at constant v. And du ds at constant v is going to equal t. By the way, that's not equal, that implies d squared u dv ds is going to equal dt dv at constant s. And what the property of state functions tells you is that these two quantities are the same. So this is our first Maxwell relation. So dt dv at constant s equals minus dp ds at constant v. So that's the first one. I'll box it. Now you should be able to get a Maxwell relation out of each of these fundamental property relations. So dH, the natural variables are going to be s and p. So I'm going to say dH ds at constant p is equal to t. dH dp at constant s is going to equal v, and d squared h dp ds is going to equal dt dp at constant s, and d squared h ds dp is going to equal dv ds at constant p. And these will be equal to each other. So our second Maxwell relation is going to be dt dp at constant s equals dv ds at constant p. Our third is going to come from the Helmholtz energy. So dA dt at constant v is going to be minus s. dA dv at constant t is going to equal minus p. d squared a dt dv is going to be minus ds dv at constant t. Oops. I should have written this as dv dt, and this follows from that. d squared a dt dv is going to equal minus dp dt at constant v. Therefore, the negatives cancel. ds dv at constant t equals dp dt at constant v. Okay, the last one that we're going to get from this set of equations is from dg. So then dg dt at constant p is minus s. dg dp at constant t is going to equal v. Therefore, d squared g dp dt equals minus ds dp at constant t, and this should be the same as d squared g dt dp, which would equal dv dt at constant p. Right, I should have, these are equal. And so the last Maxwell relation we're going to get here is minus ds dp at constant t equals dv dt at constant p. And I think we're done.